In this three-part module, we will discuss serial and parallel interfaces and how these are implemented as ports on a modern desktop computer or popularly known as PC. Serial interface part 1, that is this module, will cover basics of various types of serial interfaces and communication protocols. In next module, that is serial interface part 2, we will go into further details of most commonly used asynchronous serial interface and its practical circuit called UART. In the last and the third module, we will cover parallel interface and printer port. Let us begin our discussion with word interface when used in conjunction with computers. An interface is a shared boundary across which two separate components or parts of a computer system exchange information. For example, the parts could be the system unit of a PC and a printer or a mouse. The exchange can be unidirectional or bidirectional, that is, data and commands which would be transferred may flow in both or only one direction. Any interface has two aspects for its operations. 1. Hardware. Electrical signals carrying wires or cables, connectors, etc. And 2. Protocol. A mutually agreed understanding about permitted logic level voltages, rate of data transfer and sequence of operations required to work seamlessly. Protocols are usually implemented in hardware and software both. An interface transfers data from one block or device or module or a domain to another similar entity in a fast and efficient manner without any error. Figure 1 shows classification of interfaces used in a computer system. A computer has many interfaces, and here we will discuss the two in particular, namely serial and parallel interfaces. Let us assume that we wish to send a single character A from PC to another device such as printer or modem. The character is coded in ASCII or ASCII and represented by a 8-bit word called byte, and its value is hexadecimal 41 or decimal 65. It can also be written in binary as 01000001. The transfer of character A is now reduced to a transferring 8 bits from source to destination. Let us examine two possible ways of doing so. First, if we provide 8 wires to carry 8 bits of byte, one wire for each bit, then the interface would be called as parallel interface. Here, all the bits would travel at the same instant of time. 2. If we provide only one wire over which 8 bits travel one after another, then the interface would be called as serial interface. Here all the 8 bits would travel at different instants of time. Some bits would arrive first and some bit would arrive last. In principle, all things being equal, the serial interface would require 8 times more time than parallel interface. Figure 2 shows this concept in a diagram. Thus, parallel interface requires more wires as compared to serial interface, but it is several times faster in transferring data. When does one choose a parallel interface over serial interface and vice versa? If the distance between two blocks is small and complexity of circuits required on each wire is negligible, then parallel interface is preferred due to its affordable cost. Parallel interfaces are popular for short distances such as 10 centimeters to 2 meters or say between system unit and a printer. When the distances are large, the cost of wiring and the signal driving circuit is high, then the serial interface is preferred due to overall lower cost. The extra time needed to send bits serially is acceptable in most cases. Serial interfaces are popular between computers and modem and computers over distances up to 10 meters or even sometimes up to 1 kilometer with suitable line driving equipment. Serial interfaces are also popular with devices whose average data is few tens of bytes per second, such as keyboard, mouse, etc., where small additional delay due to sequential bit transmission is not noticeable. Let us now take up details of serial interface. As the name implies, this interface converts an 8-bit character into its individual bits and sends them over single wire. This wire or communication link is popularly called as a channel. Earlier, this link was always the wire, but nowadays it is easy to use a wireless link such as Bluetooth to transfer data between two modules, such as a computer and its peripherals. Serial interface can be categorized in two subclasses of transmission shown in figure 3. 1. Synchronous communication, and 2. Asynchronous communication. These words have been derived from the Greek word chron, which means time. In most computers, the time is measured or referenced to an internal high-speed clock signal derived from an oscillator circuit. If the bits are sent in consonance with this clock, then it is called as synchronous communication. For reliable and error-free communication, the instant at which each bit is sent must be precisely defined by sender block and must be known to the receiver block. The best way to avoid any misunderstanding is to send sender's clock signal on a separate wire to receiver. In figure 3, the two blocks or computer modules which exchange data are shown as two nodes, node number 1 and node number 2. You may treat them as a system unit of a PC and a modem or any similar peripheral such as a printer. By basic principle, the sender node has its clock, which is used to shift out the data bits through a shift register. These bits are sent to receiver. Receiver has its own clock, which it uses to load or shift in these bits into receiver shift register. The time between two successive bits is called as bit time, and inverse of bit time is defined as bit rate, that is number of bits sent per second. So, we can write an equation as bit rate is equal to 1 upon bit time. Another unit of bit rate in practice is called baud, which means number of symbols sent per second. In its simplest form, 1 baud equals 1 bit per second. Though it is not strictly true, for our current discussion, we will assume bit rate equal to baud. Most commonly, the literature refers to baud as baud rate also. In early days of mechanical teletypewriters, the most common baud rate was 50 bits per second for telegraph and 110 for teletypewriters. With the advent of electronic circuits, it reached much higher speeds, and current standard baud rates are available up to 921.6 kilobits per second or 9,21,600 bits per second. In many synchronous and high speed circuits, baud rates in megabits per second are also available. In synchronous communication, the sender's clock is sent to the receiver's node along with the data on separate wire. The receiver's clock is replaced by sender's clock or made a replica of it by a special synchronizing circuit. The sender sends out a new data bit at a particular phase of the clock, say its rising edge. The receiver clock follows sender's clock. Whenever the receiver clock has a rising edge, the receiver node anticipates a new bit arrival and captures the state of data line by storing it as a bit in the shift register. The speed at which the data transfer takes place, or data rate, is completely decided by sender's clock frequency, and receiver has no control over it. Synchronous communication is a protocol in which data is sent in a continuous stream at a constant rate. In modern circuits, it is wasteful to dedicate one wire or channel solely for the transmitter's clock. Hence, currently receivers have a local oscillators called receive clock, which is synchronized to transmit clock by special techniques by watching over the data pattern. Synchronous method is further subdivided into two protocols, byte oriented protocols. Assume that the sender node sends a long block of data. After that there is a pause and then next block will be sent. When the line is not actively transmitting data between two blocks, it is called to be in idle condition. This idle period is used to synchronize the receiver clock to transmitter clock by transmitting a sequence of synchronous idle characters. A certain number of idles are always sent prior to each burst of transmission. The IBM binary synchronous protocol, also known as BiSync, is one such old protocol still in use. Other significant examples of byte oriented protocols are IBM's synchronous transmit receive STR and digital data communications message protocol DDCMP from Digital Equipment Corporation. Bit oriented protocols. Bit oriented protocols are synchronous protocols that view the transmitted data as a stream of bits with no semantics or meaning. Control codes are defined in terms of bit sequences instead of characters. Receiver clock synchronization is maintained on an idle line by transmitting a predefined sequence of bits. Synchronous data link control or SDLC was the first bit oriented protocol developed, and it was later adopted by International Organization for Standardization, popularly known as ISO, as high level data link control or HDLC. It specifies that a node must continue transmitting a sequence of 1 bits on an idle line. Data to be transmitted on an idle line is prefixed with a special bit sequence 0, 111, 1111, 0, B called a flag. Other examples of bit oriented protocols are logical link control LLC, which is used in IEEE 802.2, and ANSI Advanced Data Communication Control Protocol ADCCP. In asynchronous communication method, the sender node sends only data and both clocks are not synchronized, hence the name asynchronous. The receiver clock does not have any relationship with frequency or phase of the sender's clock. Both nodes have their own clocks and they may be of different frequency and phase. In this method, the data is not sent in bits but in a unit, which is a collection of bits. A unit is called as a word or a packet or byte or a character. Usually there could be 5, 6, 7 or 8 data bits which are grouped together and sent. So, to synchronize receiving of a group, the data stream is preceded by a start signal and followed by a stop signal. The start signal prepares the receiver clock for arrival of data, and the stop signal resets its state to enable triggering of a new sequence. Thus, the receiver clock synchronizes itself with transmitter clock at the beginning of each transmission unit. Asynchronous method is very simple to implement in practical circuits. It saves one wire or link by not transmitting sender's clock. In addition, it saves complex synchronizing circuit and protocol deployed in SDLC and other methods. Let us look at asynchronous method in greater detail. Refer to figure 4 depicting two diagrams. The upper diagram shows the bits sent in sequence in this protocol, while the lower part shows transmission of a single character M in ASCII code of 7 bits 100, 1101 with a parity bit. The protocol has following salient features. A. The transmission of information is in units or packets of 1 character. Usually it is represented by 7 bits or 8 bits. B. The transmission need not be continuous and there can be random gap between 2 characters. C. Usually when there is no transmission, the wire or the line or the channel is called to be in idle mode. The logic level or voltage on the line is called as logic 1 or mark. D. the transmission always begins with a start bit whose voltage level is logic 0 or space. The line stays at this level for 1 bit time. E. After start bit, the sender sends least significant bit of 7-bit word. This could be 0 or 1, anything depending upon the character to be sent. F. Similarly, bits 2, 3, 4, 5 and most significant bit, that is bit 6, are sent. If the character is represented by 8 bits, then most significant bit or bit 7 is sent. G. At this point, a complete character has been sent. H. After the character, a parity bit is sent. If there is electrical noise on the line, there are chances that logic 0 is converted to logic 1 and vice versa. Parity bit acts like a protection bit which indicates presence of such an error at the receiving node. I. In many cases where the line is in short length, not very noisy, the parity bit can be optionally eliminated. J. The end of transmission unit is signaled by a stop bit. This is logic 1 or mark. Note that stop and idle have similar levels. Thus, stop bit allows receiver to return to the same idle state which it was initially. K. Sender and receiver always have a prior understanding of certain parameters such as number of bits per character, 5, 6, 7 or 8 bits per character, comma, number of stop bits 1 or 2, comma, presence or absence of parity bit, etc. The bit time is also prearranged for both clocks. In summary, the transmission of one character requires overhead or extra expenditure of minimum 2 bits, 1 start bit and 1 stop bit. Thus, to send 8 data bits, we must send 8 plus 2 or 10 data bits. This results in an overall efficiency of 80%. Addition of parity bit further decreases the efficiency. Now, the receiver works as follows. A. It is at idle state. When the start bit occurs, the line makes a high to low transition. The receiver clock synchronizes itself at this point. B. After half bit time delay, during the middle of the start bit, it checks again the line condition, that whether it is still space or logic 0. If it is still 0, it proves that it is a valid start bit and not a spurious low level pulse on the line. C. After 1 bit time, the receiver is approximately into the middle of the first bit or LS bit center. It samples the voltage as 0 or 1 and stores it. After another 1 bit time delay, receiver is approximately in the middle of bit 1's center. It samples the voltage level as 0 or 1 and stores it. It repeats for all bits till most significant bit is received. Now, all bits of the character have been collected and stored. After another bit time delay, receiver is sampling approximately in the middle of parity bit agreed upon mutually or stop bits center. It samples the voltage level and stores it. If the receiver does not find the level as mark or 1, then it is termed as framing error. F. Since the sampling is in the middle of the bit time, for each bit there is a margin of half bit time on either side. If the receiver and transmitter clock frequencies are not the same, but there is a difference or error, then the receiver will sample either slightly later or slightly earlier than the middle of each bit time. Since this error is cumulative error, cumulative over 8 plus 2 plus 1 or 11 bits, the maximum deviation acceptable over 11 bits is half bit time, which is roughly 0.1 divided by 11 or 4.5%. Thus, the receiver will successfully read 10 bits, 8 data bits plus start and stop bits, even if its clock frequency is 4.5% away from the sender's clock frequency. The lower part of diagram in figure 4 shows transmission of character M. It is represented by 7-bit ASCII code 100 110 1101. It is represented by 7-bit ASCII code 100 1101. The parity bit selected is even type, and for this character parity bit is 0. Note that first a start bit which is 0 is sent. It is followed by LS bit or bit 0 which is 1, then bit 1 which is 0, bit 2 which is 1, bit 3 which is 1, bit 4 which is 0, bit 5 which is 0, and at last bit 6 or MS bit which is 1. After that the parity bit which is 0 is sent. The transmission is completed by sending stop which is 1 bit. This method of sending LS bit first is called little endian method. This brings us to the closure of serial interface part 1.